So now this is the last week and we are going to look at topos theory. So the word topos is a Latin word. It literally means space. And there are different interpretations of what a topos is. So let me begin with a story from our culture. So suppose there are 3 or 4, there were, if I have to tell a story, it should be in the past tense. So there were 4 blind men from birth. So those 4 blind men, they wanted to feel what an elephant looked like. Wanted to feel an elephant, okay, simple. And then one elephant was brought close to them and they touched different parts. One blind person said, an elephant is like a tree. Another blind person said, it's like a broom. Another said, it's like a snake. So they were touching different body parts of that elephant, but because they were blind, they couldn't really get the entire view. And for this reason, you cannot really get an entire idea about an elephant if you only have a local viewpoint. Same thing, this is actually the beginning paragraph of the preface of a book on this subject, on topos theory. So the title is apt. It's Sketches of an Elephant, a topos theory compendium. So topos theory can be thought of as different things. It can be thought of as a generalized space as in topological space. It can be thought of as a generalized universe of sets. It can be thought of as a classifying space for theories. So there are so many, and if you read, like I'm not going to give you an entire list, there are 10 notions coming which appear in this preface. But I'm not going to follow that book that it's a topos theory compendium, it's like an encyclopedia. So I'm not going to follow this entire encyclopedia. I would rather follow another book. So it's not by the same author. So the Sketches of an Elephant is by Peter Johnston. I mentioned him also in the first lecture because I learnt this subject from him. So this second book that I'm talking about, it's called Sheaves in Geometry and Logic. This is by MacLean and Mordyke. All of you are familiar with MacLean already. And the second name is E.K. Mordyke from, I think, Netherlands, from the Netherlands. So this is the book that I'm mostly going to follow. But of course, since there are only 2 lectures, I cannot say a lot. I will try to explain different ideas. So the concept of a topos was introduced. I mean, the definition itself was given by Grothendieck, Alexander Grothendieck in 1963. So before Grothendieck, there were quite a few people. So Grothendieck gave a definition in 1963. And so this is the definition for one type of a topos, and that topos is called a Grothendieck topos. Of course, he did not name it a Grothendieck topos. People later started calling it a Grothendieck topos. So this is the idea of a generalized space. To give you some background about this, I'm going to tell you some results which you may not know, but nevertheless they have been motivating examples in this context. So now imagine a projective space over complex numbers, projective variety. So let's consider simple projective variety. the P1C. P1C is like you have a projective line, so complex line is actually the complex plane, and then you have to add P0 to it. I mean, it's A1. A1 is the affine space, one-dimensional affine space, and then you close it, you take its one-point compactification, that becomes your projective space. The appropriate notion, so this is a concept in algebraic geometry, so we are talking about algebraic variety, so this is a projective variety. It has a Zariski topology defined on it, yeah, where all non-empty open subsets are dense. Yeah, so they are very large. All non-empty subsets are very large and the closed subsets are very small. They are strictly lower dimensional. So, the appropriate notion of a morphism between varieties is that of a regular map. Regular maps are, you can think of them as locally, they are ratios of polynomials, but they are defined everywhere. So, one interesting result from projective varieties is that the globally defined regular functions on a projective variety over complex numbers, I am taking this, otherwise the result fails to be true, is, I mean, the ring of globally defined regular functions on a projective variety over C is just C itself. So, only constant functions are the globally defined regular functions. But if you remove at least one point from it, so you go to its its affine subvarieties, then there are far more regular functions defined, which means you would like to consider the data of regular functions which are partially defined, which are defined only on open subsets. Okay, if you do not know, I mean, this is a motivating example, but even if you do not know, I will give you some other example. You can think of just continuous functions. Okay, so continuous functions defined on a topological space, and you can also consider continuous functions defined on open subsets of the topological space. So regular functions are just the appropriate algebraic geometric analogues of continuous functions. Okay, so one example is like this. So given a topological space X and an open subset U of X, consider Fu to be the set of all continuous C-valued functions on U. Okay, just this data. Now, this particular data comes equipped with some natural morphisms. So, for example, if V is a subset of U and V and U are both open, then F mapping to F restricted to V from Fu to Fv is a well-defined map. Any questions about this? If F is a continuous function from U to C, then its restriction to V is a continuous function from V to C. Correct? So this particular restriction map, which I may want to call as rho VU. Okay, so it's the restriction map from U to V is a well-defined function, and rho UU is identity on FU. So the restriction of a continuous function on FU to U is just F itself. Nothing really changes. Any problems so far regarding this definition? So this data, the data that FU is the set of all continuous C-valued functions, and FU to FV there is a map, restriction map, which satisfies this property, and the restriction map is composes to give another restriction map, right? If I restrict from U to V and then V to W, then that is same thing as restriction from U to W. So this is your prototypical example. Moreover, also observe that it, even though I am calling it just a set of continuous C-valued functions, it is actually a vector space. It is a C-valued, like it is a C vector space, complex vector space. I could have talked also about just an abelian group of the abelian group of all continuous C-valued functions. I could have talked about the vector space of all continuous C-valued functions. I could have landed inside any category, but this data is important, the restriction map. This is your prototypical example of the so-called pre-sheaf. Okay, so this is an example of this data is an example of a pre-sheaf on X. So what is a pre-sheaf on X? Well, basically you can see this is simply a functor. What we are doing, so recall that OX denotes the poset of all open subsets of X with respect to inclusion. Okay, so F is doing what? F is taking every element of OX and mapping it to a set. So this has to be a functor from OX to sets. Yeah, so therefore F is a functor from OX to sets. But whenever I have V contained inside U, then the restriction map actually goes in the opposite direction. So which means it is a contravariant functor. So I have to put an op over here. So it's a contravariant functor. A pre-sheaf on a topological space is simply a contravariant functor on the poset of its open subsets. Nothing more. Okay, so this is the definition of a pre-sheaf. More generally, okay, a pre-sheaf on a skeletally small category C is simply a contravariant functor on C. Okay, so more generally, a pre-sheaf on a skeletally small, I mean in practice we are just going to choose this to be small, a skeletally small category C is a contravariant functor on C. Okay, so therefore the category of pre-sheaves So they also, like in sheaf theory, you also define a morphism of presheaves, but that is just a natural transformation. We are not doing anything fancy over here. So the category of presheaves is C hat, which is defined to be the functor category C offsets. Okay. Now, this is just a definition of a presheaf. Nothing is really happening. If you want to talk about a sheaf, then that certain presheaf will have to satisfy some extra conditions. Now, what are those conditions? Okay, so let me use a different color. The sheaf condition. So a presheaf like F belonging to OX hat is a sheaf if star holds. If the following condition holds, if given any open cover UI, all of you understand an open cover? Open cover UI of U? What is happening here? Tell me. Union of UIs is it covers U, or here you can also think about union of UI being equal to U. Okay. So given any open cover and any sections, the individual elements are called sections. Yeah, the individual elements of the set FUI are called sections. So any sections FUI satisfying compatibility conditions So what is the compatibility condition? That Fi when I restrict it to UI intersection Uj, that is same as Fj restricted to UI intersection Uj for all I and j in I. So I am given some collection of, I am just going to talk about continuous functions. So I am given some continuous functions on each UI, such that whenever they agree, whenever their domains intersect, then the functions agree. Then, so this is all the data. Then there is a unique continuous function on the entirety of U, such that F restricted to UI is Fi. So all these individual sections can be glued to get a unique continuous function on the open set, on the full open set. If, okay, now think about this, if I change continuous functions to bounded functions, then the sheaf condition will not hold. You understand? Suppose I am taking the open interval minus 1 by n to plus 1 by n for different n. That will form an open cover of minus 1 to 1. Now if I take the function, or maybe just 0 to 1 by n, 0 to 1 by n, and I take the open cover, and the function is 1 over 1 minus x. 1 over 1 minus x. Now that is bounded on each of the open subsets, but will it be bounded on the entire open 0, 1? It will no longer be bounded. So bounded functions do not form a sheaf. That is still a presheaf, but it's not a sheaf. But continuous functions, on the other hand, they do form a sheaf. So there are two things here. Yeah, in the sheaf condition, I am talking about two different things. First one is saying that there is a gluing, there is an amalgamation. And the second condition says that such an amalgamation is unique. You understand? So sheaf condition has two different parts. Any questions? Continuous on? 1 over 1 minus x, yes. That is continuous, yes. But it's not bounded. I said that if my f is the set of all bounded functions on that, yeah, I changed the pre-sheaf. Yeah, so continuity was replaced by boundedness. Then it doesn't remain a sheaf. But here it is definitely a sheaf. Continuity will give you sheaf condition. Okay, so that means the collection, the subcategory, the full subcategory of pre-sheaves on X satisfying the sheaf condition is denoted sheaf of X. These are all French words. Okay, so the word sheaf is also French. I will talk about many more things later. In general, also for C hat, like the functor category from C op to sets, you will have some subcategory of sheaves. But it is not clear what that part is, correct? What the sheaf condition should be. Because for sheaf condition, you need the concept of an open cover. Well, if I change it to arbitrary category C, I do not have a notion of an open cover because there is no topology. This is the part where Grothendieck's genius came into picture. Grothendieck defined a topology on a small category. It's called a Grothendieck topology. And with respect to Grothendieck topology, there can be multiple Grothendieck topologies on the same small category. And then he said that you can take sheaves with respect to that topology. And then that will form a subcategory of the category of pre-sheaves. And then that will be called, like all these categories, the category of pre-sheaves, the category of sheaves, these are all examples of toposes. So following Latin convention, sometimes people call it topoi, but I'm just going to use the English convention of calling it toposes. The plural will be toposes. Okay. Now I will also tell you some background, some history. One point of history was, of course, what I said earlier, that the ring of globally defined regular functions is C. But then if you want to study some polynomially defined functions or rational functions on projective varieties, are you not going to do it at all? Like only constant functions are good functions. But the answer is no. You would rather study regular functions defined on open subsets. Open subsets are dense, so that's also nice, like except for finitely many points or except for a smaller dimensional subvariety, you can still define them. The main motivation for all this, okay, came from work of Cartan and Oka. So this was from 1944. What they were trying to do is, there was a book of Weil, Hermann Weil. Hermann Weil also gave some conjectures. I will also talk about them. So Hermann Weil's book on Riemann surfaces, yeah, in which like that contained the idea of a Riemann surface, and Cartan and Oka, they were working on this particular topic. In complex analysis, several complex variables, to be more precise. So while they were working on several complex variables and holomorphic functions defined on them, okay, so then they were interested in analytic continuations of holomorphic functions defined on certain domains. If you know what that means, analytic continuations, like at every point there is a Taylor series expansion and then you would like to extend this function in such a way that the Taylor series expansion is still valid. So this was the original motivation for the definition of a sheaf. So what Kartan and Oka they did was they studied coherent systems of punctual ideals. Okay, the words are not important, punctual ideals are not important here. The word coherent system is important. Coherent system means it should behave nicely with respect to maps. And that is precisely the condition of pre-sheaf and sheaf. So the origins of the concept of sheaf, they were coming from this, also coming from algebraic geometry, as I already pointed out. And immediately after World War II, Jean Leray, he came up with the concept, he came up with the definition of a sheaf on a topological space, but he used closed subsets instead of open. Then it was later modified by Kartan so that it became a definition using open subsets, which is what I just presented to you. It can be a sheaf of abelian groups, it can be a sheaf of vector spaces, sheaf of rings, anything is possible. What you have to just vary is C op to what? C op to sets, well, that's just a set valued pre-sheaf or a sheaf. If you change it to ARP, then you will get a sheaf of abelian group, sheaf of vector spaces, rings, any algebraic category would work at that point. And then these things kept popping up at several locations. So eventually Grothendieck formulated this definition because there was also some work in algebraic topology when Eilenberg and Steenrod, they had given some axioms for general cohomology theory. We have already seen some cohomology definitions, at least we haven't seen cohomology theories, but definitions. And what they wanted to do was cohomology theories with variable what is it called? Variable variable coefficients, correct, yeah. Cohomology theories with variable coefficients. So all these ideas were about some coherent systems of data, but that data had to satisfy certain extra property, and that property usually came from this. However, like there was also some other things. So Grothendieck found out that you don't really need the concept of a topology to be present. You can generalize it to any category, and therefore he gave a definition of a topos or a sheaf. Grothendieck topos is the category of sheaves on a Grothendieck site, like a category of sheaves with respect to a Grothendieck topology. I haven't defined a Grothendieck topology, so I won't write it down yet. I will do it by the next lecture. And around the same time when Grothendieck came up with his idea, then from algebraic geometry, there was another concept that a sheaf is just an étale map into that topological space. So if you know these things, then they are the same. Yeah. Now, at that time, Grothendieck had taken a break for some time and he had become a farmer. Okay, he was fed up of the mathematical world for some time Yeah, Grothendieck's biography is very interesting. It's an autobiography. You recall the semi. I highly recommend you to read it, but it's in French. Yeah, there are some translations available, but they are not yet very good. So in Recall the Seme, he says that he was a farmer at that point, but he was still thinking about mathematics, and he started thinking about this problem during that part. So therefore, the entire terminology of sheaf theory actually comes from agriculture. So we have terms like sieve, you understand? Yeah, something through which you filter things out. Only certain things are allowed to pass through, the rest, the larger pieces have to be retained. Then stalk, germ, sheaf, crible. Yeah, so there are so many things which come from agriculture. All this terminology comes from agriculture. And this concept of a generalized space or sheaves on a generalized space, which we now call a Grothendieck topos, this was used later in 1974 to settle Weil's conjectures. Hermann Weil, I already spoke about him. So Weil's conjecture in the affirmative by Pierre Deligne. Deligne was a former PhD student of Grothendieck, and they also had a rivalry because of this particular point, that Grothendieck wanted to develop this theory further, and he never really wanted to solve a problem by making it the entire goal or solve a conjecture. His philosophy was different. He always wanted to expand the horizons such that the problems will automatically get solved. But Deligne went in and he used Grothendieck's machinery to solve Weil conjectures, and then I think they never spoke to each other properly ever after that. Okay, so let's come back to this history part. Simultaneously, okay, 1963, that was also around the same time when Paul Cohen, he gave a proof of independence of continuum hypothesis and axiom of choice from the rest of the axioms of Zermelo-Fraenkel set theory. And the ideas that he used, the technique is called forcing, and the forcing technique was also becoming, I mean, it was popular. So see, it was already shown by Gödel in 1930s that continuum hypothesis does not contradict the rest of the axioms of Zermelo-Fraenkel set theory. But it wasn't really clear for around 20 years whether it follows from the remaining axioms, whether it is a consequence of the remaining axioms or not. But Paul Cohen settled that question, saying that no, it is not a consequence, it is completely independent from the rest of the axioms, and so is axiom of choice. The techniques that he used, the forcing technique as we call it now, that had striking similarities with the concept of a sheaf. So around the same time, Laver, he also came up with a definition of another type of a space. So Laver and later Tierney, they gave a definition of an elementary topos. So because its motivation came from set theory, elementary topos was supposed to capture a generalized universe of sets. So an elementary topos was defined as the category which has all the nice properties of the category of sets. Okay, so that was another thing. All Grothendieck toposes are elementary toposes, but not vice versa. Okay, so there are far more elementary topoi or toposes compared to Grothendieck toposes. Okay, so I mean, an elementary topos is very easy to define. It just needs three concepts. First of all, it's a Cartesian category. Can you tell me what a Cartesian category is? All finite limits exist. Second one, it is closed as a Cartesian category. Closed monadal categories, if you remember, the product functor has a right adjoint. Okay, so that is the exponential functor. So exponentials exist, right? And the last one is that it has a subobject classifier. I will talk about it. So subobject classifier is like the universal subobject, universal monomorphism, such that every other monomorphism in the category is a pullback of it. Okay, so that's the subobject classifier. So this is an elementary topos, and every Grothendieck topos is also an elementary topos, but not the other way around. So of course, I mean, the category of sets is an example of an elementary topos. It's also an example of a Grothendieck topos. Okay, now enters a third entity, third person, yeah, that is Kripke. So Kripke was trying to study, I mean, he is a well-known figure for studying modal logic, semantics for modal logic. But Kripke was, while he was studying intuitionistic logic, of Brouwer. Brouwer, you have probably heard of the name, Brouwer's fixed point theorem from topology. So Brouwer gave this concept of intuitionistic logic, which is essentially classical logic minus proof by contradictions. Okay, so proof by contradiction means what? That I want to prove a statement P, but I will start with negation P, then I will arrive at a contradiction, and therefore I will conclude that P is true. So what it assumes is either P holds or negation P holds. There is no third possibility. So intuitionistic logic, that is classical logic minus law of excluded middle. So law of excluded middle means, if I have to write it properly, it says that P or negation P is a consequence of truth, means it is always true. So if you remove this, because most people do not want to work with this, so when you remove this classical from the classical logic, you get so-called intuitionistic logic, and the algebras that you get for classical logic are called Boolean algebras, whereas the corresponding algebras in intuitionistic logic are Eyting algebras. And Eyting algebras, as we have already seen in this course, they are Cartesian closed distributive lattices. Correct, very good. So they are so the meet functor has a left adjoint, namely the implication. We have seen this in the course. So what it turns out is that if you are given any elementary topos or any Grothendieck topos, then the subobject posets of objects, first of all, they are sets, and moreover they have a structure, they have the structure of an Eyting algebra. So the actual formal statement here could be termed as intuitionistic logic is the internal logic of a topos. Okay, internally this happens. I will talk a bit about internal versus external later on, what I really mean. That the subobject lattices are Eyting algebras, and moreover there is also an internal Eyting algebra on the subobject classifier, which is the universal such amongst all these. Okay, so because of that reason, so I mean Kripke's ideas, Kripke's semantics, it can, for intuitionistic logic, it could be used at that time to find a model of set theory, let's say, or a topos with a real number object such that every function from reals to reals is continuous. Okay, so real number object can be abstractly defined, natural number object can be abstractly defined, and there exists some model of set theory in which there is a real number object. I'm not saying real numbers, I'm saying real number object such that every function is continuous. Well, this is the beginning of the so-called synthetic differential geometry. We are doing differential geometry, but only axiomatically. There is no real space underlying it. So this was originally Kripke's idea for semantics for intuitionistic logic, which makes it possible. So corresponding to this, yeah, I mean now that we have talked about this, so Kripke semantics eventually led to synthetic differential geometry. Okay. So in topology, usually there is a concept of a classifying space, or I mean classifying space functor. I think we briefly talked about that in the past week while discussing simplicial sets. But this is in, if we are studying vector bundles, if you know, vector bundles are like, they are continuous surjective maps. Like a vector bundle over X is a continuous surjective map F from Y to X such that F inverse of X is a vector space, is a, let's say, is a C vector space of finite dimension. Yes, of finite dimension, and for all X in X, there exists a neighborhood U of X such that, neighborhood means open neighborhood, such that F inverse of U is homeomorphic to, let's say of dimension n, C to the power n cross U. Okay, I'm just talking about complex things here. Okay, so this is a vector bundle, and the classifying space for vector bundles is another vector bundle is some E to B such that every vector bundle, like the collection of vector bundles on X, is in one-to-one correspondence with maps from X to B. So what happens here is simple actually. So you have this E to B, and then given any X to B, you can always take a pullback. And this is happening in the category of topological spaces itself. So the pullback of this epimorphism will be an epi, and you will get this. Moreover, This is not the interesting part, but the interesting part is that given any y to x, a vector bundle, there will be a map, the classifying map for this y, which will be a map from x to b. So every vector bundle on x is obtained in this particular fashion. This idea is really important. So this is the, like, E to B is said to be the classifying space for vector bundles. This is like the characteristic map, yeah. Even in set theory we do this. Subsets are in one-to-one correspondence with maps from the set to two element set. Okay. So in a similar spirit, yeah, in a similar spirit, okay, given any mathematical theory, so given any mathematical theory like the theory of groups, so theory of groups has three axioms: associativity, inverse, and identity and inverse. And we can write this theory down as a commutative diagram. We have done that while discussing monads, right? So given any mathematical theory, the models, I mean, there is a spatial topos BT with a spatial object R in BT such that the category of models of T in a topos E is in 1-1 correspondence is equivalent to the category of morphisms from E to BT. If I have to write it succinctly, then I will do it this way. The E models of T. So when I take E, so I already told you sets is a topos. The category of sets is a topos. So the models of this theory in the category of sets, what will they be? Simply the ordinary groups. Models of the theory of groups in the category of sets are ordinary groups. If I change the category, then there will be something different. I haven't made this precise, but you can understand what I am saying. There is a category of models of T in E. This is equivalent to the category of morphisms. Now this category of morphisms is called the category of geometric morphisms from E to BT. The appropriate notion of a morphism between two Grothendieck toposes is that of a geometric morphism. Okay, so where I have to define what a geometric morphism is. Where a geometric morphism E to E prime is a pair of adjoint functors. Okay, let me write it appropriately. So like this. This is my left adjoint, this is my right adjoint, F upper star, F lower star, such that F upper star preserves finite limits. So the left adjoint is left exact. Does that ring a bell? It's an adjunction where left adjoint preserves finite limits. It's left exact. Localization, correct, very good. So we have already seen such examples in the in the additive world. Okay, so these are also like that. So what is the mapping here? Yeah, if I'm given a morphism here, so f upper star, f lower star, then what is the functor doing here, the equivalence doing? It is sending it to, sorry, f lower star, I should write it properly, f lower star. The model that we want is actually f upper star of R. So every model of theory T in category in the topos E is of the form f upper star of R for some left part of the geometric morphism. So such a thing, this spatial topos is actually called a classifying topos. Okay. So classifying toposes, there is a theorem here now, and I'm obviously not going to prove it, that Grothendieck E is a Grothendieck topos if and only if it is a classifying topos. So the notion of classifying topos originates in logic, whereas the notion of a Grothendieck topos, it originated in geometry. Now perhaps you will appreciate the title of the book, Sheaves in Geometry and Logic. Yeah, so this book will talk about topos theory from two different perspectives, and it also discusses elementary toposes. Right, so geometry gives us Grothendieck topos, set theory gives us, like foundations give us elementary topos, and logic gives us classifying topos. So these are 3 of the 10 things mentioned there. Okay, we have very different motivations, but they all seem to converge. Any questions so far? Okay. So now perhaps we can start talking about something more concrete. I haven't even defined anything so far, so let me start with that. The first part that I'm going to cover is that of an elementary topos. Okay. A category E is said to be an elementary topos if this is not the textbook definition, that will be a slightly toned down, like they will eventually come at this definition, but I'm going to write it anyway, is an elementary topos if it is a Cartesian closed category with a subobject classifier. Okay, so subobject classifier is the thing that I need to discuss. So a subobject classifier is a monomorphism one to omega, and its label is true. It is the true map. So this is a monomorphism such that every monomorphism in E is a pullback of true. One you understand, one is the terminal object. Omega is the object that you are required to exist. And true is a monomorphism, it is a specific monomorphism. I mean, many times what happens that, as is common with category theory, that object omega is called a subobject classifier. No, it is the object omega together with a choice of map, choice of a monomorphism, such that in every mono is a pullback of true. Okay, so how is it a pullback of true? So given
Given a fixed category E,
uh-huh.
can the omega vary or?
No, given a fixed category E, the omega is fixed. Yes. So given any monomorphism, there is a map, there is some chi m, I am going to call it chi m, the classifying map from B to omega, such that this is a pullback diagram. So the exclamation mark is obviously the unique map to the terminal object, and pullback of a mono is mono always. So this is the universal mono. Everything is a pullback of this universal monomorphism. So chi m notation, it comes from the characteristic function from set theory. Yeah, here for change, okay. So in sets, for example, in sets, omega is 0, 1, and true, this is a convention which I am going to follow. True is true from 1 to omega has image 0. Yeah, not 1. I mean, I'm just formally inverting the values, but because then things become easier later on. So what is the characteristic function? So given any B prime subset of B, chi of B prime is from B to omega is defined by little b mapping to 0 if B belongs to B prime and 1 otherwise. This is not necessarily the standard characteristic function that you are used to, but I am just swapping the roles of 0 and 1.
If we have taken this image to be 1,
Then also it will be true. Then also it will be true. Like that can be treated as a universal thing. But when I'm going to construct more complicated categories from it, I would rather have this. So the category of sets is clearly Cartesian. It has finite limits. Then it has exponentials. What are the exponentials? B to the power A is the what is B to the power A in the category of sets? The set of functions from A to B. A to B, yes. Because it's still a set. It's self-enriched, yeah. So it is still a set, so it is Cartesian closed and it has a subobject classifier. Now conversely, if you are given any map from B to omega, then obviously you can get a monomorphism. This other thing, by just pulling back the true morphism, this other thing is more important. Yeah, that given any monomorphism, there exists a map such that this is a pullback. Okay, so let me try to write the same thing in a slightly different language. So therefore, sub E of B is in bijection with the home set from B to omega. And this implies that sub E blank is representable. This is representable, right? Sub is actually a contravariant functor and it is representable. What is the representing object? Omega. And you also need an element. So think about that. If any functor is representable, then what you do? Okay. So sub E is representable, and moreover, there is also another functor that is representable. Moreover, I mean it's not following from this, but E B cross blank comma omega is also representable. Why? Since E of B cross A, what does that give you? Yes, E of B, A comma power set of B. Well, I am just going to write it as omega to the power B. This exponential exists. Now define P of B to be omega to the power B. This is the power object. If you know the axioms for Zermelo-Fraenkel set theory, then one of the axioms says that for every set there is a power set, right? So this is that power set. So you are saying that for every object there is a power object, namely omega to the power B, which has all the nice properties. Okay, let's see what we are doing. So with PB we can also do this. So we have this epsilon, perhaps I should do the membership operation from B cross PB to omega. What is this membership? Can you tell me how this operation is arrived at?
If x belongs to A, then x comma A will map to.
Yes, if x belongs to a subset B prime, then x comma B prime will map to true. Otherwise it won't. That's the set understanding. But how do you obtain this map? The membership map. Yes, is the image of what? XF and F. Yes, but can you tell me how to obtain this? The notation epsilon in category theory, what does it shout at you? The co-unit, So this is the co-unit of that. So corresponds to PB to PB identity map under the adjunction. Right, because PB is omega to the power B. So you are just bringing this B to this side. And this is the membership map. So now even though there is nothing like an element, you still have elements. The membership relation. Similarly, yeah, the singleton map also exists. This is the map from B to PB. What does it correspond to? So this corresponds to the unique map. Now we are taking it just one level up. B cross B to omega, which is actually the characteristic function of diagonal, which corresponds to the map from B to B cross B, the diagonal embedding. This is the diagonal embedding. So there are two adjunctions and we are combining those two adjunctions in this form. The singleton map comes from the classifying map of the diagonal, or the Kronecker delta, you may call it. The diagonal map is also the Kronecker delta. And Kronecker delta and this classifying map, they correspond to each other under the first adjunction, the first correspondence, the subobject going to the classifier, classifying map. So there is also a notion of a singleton map. The omega here actually, yeah, the omega is supposed to denote the collection of truth values. In classical logic, how many truth values are there? Only two, true and false. So the true is 0 as per our convention and 1 is false. But what is happening here? Omega in any category, that will be the collection of truth values. One of them will be true. We will see how to find the false one. Yeah, the false one, I mean, maybe I can show you. Yeah, the false one is simply like 0 to 1 is always a mono. Correct? The map from 0 to 1 is a mono. And here you will have a unique map. This is the unique map, the same one. And take truth here. Then its classifying map. This is the false map. The false map is the classifier of the trivial subobject of 1. This will also turn out to be a monomorphism, obviously.
So in general, for any mono from 1,
For any mono from 1 to what?
1 to omega, if we do this process, then we get the negation of that truth value.
If you compose it with this, then you will get a negation. Well, I will show you some internal versus external, that thing I will show you.
Do we know that the delta map exists from B to B cross B?
Because from B to B, you do have two maps. One is the identity and the other one is identity. Delta is the factorization through the limit B cross B. B cross B is the product. So therefore, as long as you know both these individual identity maps, there must be a unique factorization through B cross B. That is the Kronecker delta. So the classifying map will give you, which transposed via that adjunction will give you the singleton map. Yeah, very interesting ideas over here. So
What about B cross B not being defined uniquely up to equality?
B cross B not being defined, like that's irrelevant, right? So all these adjunctions or all these natural these bijections are natural in all the components. I'm suppressing lot of data because I'm just talking about toposes in 2 lectures. So both these bijections here, they are like this bijection, sub and E B omega, and this bijection, they are natural in all the components. So naturality will take care of that. So omega is meant to be the collection of truth values, and omega is supposed to give you that internal Eyting algebra structure. Okay. So internal Eyting algebra is a distributive lattice where meat has a right adjoint. Every meat with a specific element has a right adjoint. If you remember that, then I will show you. First of all, let me show you how to construct certain things. Okay, some properties of elementary toposes. That's what we are doing now. So each mono is regular. Because if I am given a monomorphism M from B prime to B, then I can write it as I can take this classifying map of this, and on the other hand I can take the true map composed with the unique map. Okay, so this is an equalizer diagram. So therefore each monomorphism is indeed regular. Regular means it is the equalizer of a pair of morphisms. Okay. And therefore, if I am given a monomorphism that is also an epimorphism, then it is regular mono plus epi, and what does that imply? Regular mono plus epi is an iso. So therefore, this implies that a topos, an elementary topos, is balanced. The exponentials a to the power b have usual properties, are called internal homes. And have all the usual properties. All the usual properties, what do I mean by that? Like a to the power b1 plus b2, where this is, okay, maybe I shouldn't say this right now. I haven't yet proved that co-limits exist. So a to the power 1 is isomorphic to a, that much I can say. Then a to the power b1 cross b2 is isomorphic to a to the power b1 to the power b2, and etc. Okay. Then any questions? Okay, the power set is actually a functor. In exponent, it's always contravariant. So P from E op to E is a functor. What does it do? It takes B and maps it to omega to the power B. Hopefully you can convince yourself that this is true. This is a functor, contravariant functor, with left adjoint P op from E to E op. Okay, the same functor works as the left adjoint as well. You just have to write it slightly differently. Moreover, now this is the hard part, this adjunction is monadic. Do you remember what monadic adjunction means? EM comparison functor is?
Induces an equivalence of categories.
Yes, is an equivalence of categories. Very good. Yeah, so this adjunction is monadic. So what will happen? So let T be the monad induced by, okay, induced by this adjunction. Okay. Now let me write this. E op, you have an adjunction here. Then here we have ET, the category of EM algebras, Eilenberg-Moore algebras over this. So which one is left adjoint, which one is right adjoint? Tell me. The free functor is always left adjoint. Okay, and what is this? E to E op, that is P, and this is P op, and it has to satisfy the same kind of relation. Or maybe I am making a mistake here. Sorry, E op to E is P. Yes. So this is P and this is P op. And then there is an Eilenberg-Moore comparison functor K, which is an equivalence of categories. Okay. So recall, I mean, for this, like proving that this adjunction is monadic, we need to use monadicity theorem, Beck's monadicity theorem, if you remember. But this, do you remember that the adjunction, this forgetful functor, so recall that the forgetful functor GT from FT, sorry, from ET to E creates all limits present in E. This we have seen, yeah, that this forgetful functor creates all limits. So what is present? E is an elementary topos. So what is present in E? All finite limits. So this GT will create these limits. So therefore ET will have all finite limits, and this functor will preserve them, GT will preserve them. So ET has finite limits, which means the equivalent category E op also has finite limits. What does that tell us about E? That E has all finite colimits. So you can see how beautifully we obtained all finite colimits from all finite limits. So therefore E has all finite colimits. Okay, just because of monadicity. Okay, so now an elementary topos has more structure. It has finite limits, finite colimits, and subobject classifier. Then the next one is that image factorizations exist in E. Okay, how do we do that? Now that we have shown that it has finite colimits, we can talk about push-outs. So given f from A to B in E, construct its co-kernel pair. What is the co-kernel pair? You take A to B and A to B, same morphism FF. The co-kernel pair is the morphism G comma H that appears in this push-out diagram. Then what do we know? Well, this is A to B, and now I have a pair of morphisms G and H. I can take its kernel, equalizer, not kernel. I can take the equalizer of this, and I must factor through this. The map F must factor through this. The kernel is always a mono, and it takes some work to show that this other factorization A to K, that is an AP. Okay, so this gives us an image factorization. Okay, so F can be written as M composed with E, where M is a mono and this is an AP. Okay, so image factorizations do exist here. Now I can add, actually, like after this, I can add some properties to this, that a to the power b1 plus b2 is isomorphic to a to the power b1 cross a to the power b2. And I can also add that 0 to the power b is isomorphic to b. B to the power 0 is isomorphic, a to the power 0 is isomorphic to 1. All these properties of exponentials of numbers, they are true here up to isomorphism. 0, yeah, 0 to the b is isomorphic to 0, obviously. And I also use 0 like over here to tell you what the false one was, false map was. I assume that that initial object exists, but I showed it. Okay, now I will show you how to define the external and internal meet operations in the subobject lattices. So lattice structure of sub E C for C in E. So it's a lattice. I'm not going to show the entire Eyting algebra structure, but at least the lattice structure I can show you. So if I'm given, if C1 and C2 are two subobjects of C, how do I define the meet of these two subobjects? Minimum element greater than this, but I don't know how high it should exist. You are telling me the definition of the meet, but how to construct it? What does the diagram suggest? Pullback. You take the pullback. Okay, so this is the C1 intersection C2. Pullback of a mono is mono, so this is like this diagonal is your intersection. If this is M1, this is M2, then this is M1 meet M2. So this is how you obtain the intersections of two subobjects. You should also be able to define union of two subobjects. Okay, for union, do this. So C1 and C2 are given. Then C1 plus C2, we already know there are maps, right? This is the co-projection nu1, nu2. We have been using it for a long time. Then from C1 and C2, okay, so look here that because C1 plus C2 is the co-product, there must exist a unique map through this. Let me call that M. Let me call that not M, but maybe G. Then factorize, take the image factorization. Take the image factorization of G. So what do? We have C1 plus C2, and then we have C, then I have to take a surjection onto something, and this is our C1 union C2, and then there is an inclusion. So this is actually the M1 plus M2 map. So that's how you have lattice structure over here. Now, this is the external lattice structure. Yeah, this is the so-called external lattice structure. And there is correspondingly, there is an internal lattice structure. So the internal lattice structure so if you remember, what is an internal group? Internal group is an object of your category together with a morphism from G cross G to G and a morphism from 1 to G, which is supposed to take the identity, and a morphism from G to G which corresponds to inverse, which satisfies certain commutative diagrams. So similarly, the internal lattice structure should be that there should be, like, I am just going to show the meet semilattice structure here. So there should be some meet operation from omega cross omega to omega, and there should be something like the top element, and the top element should be true. This is the largest sub-object, and then you can add other things. So this will become an Ising algebra internally. So I need to find the internal map, internal meet map, internal join map. And how do we do that? Yeah, so it's a very beautiful way of converting the external into internal and vice versa. So given any object B of the elementary topos E, what do we have? Well, we have sub E B cross sub EB. This is in like from here to here we have the intersection map going to sub EB. Given two sub-objects, I can take their intersection. This is just the pullback map. This is the external map. But this is in bijection with what? Well, sub is a representable functor, or to be more precise, co-representable, because it's the contravariant thing. So this is EB omega cross EB omega. But a pair of maps from B to omega is nothing but just a single map from E to omega cross omega. Okay. And over here, this is EB omega. This is simply the universal property of products. Now, this diagram is supposed to commute because everything is up to like there is only one map here, everything else is an isomorphism. So, this is the map meet sub B, and choose B equal to omega cross omega and identity on omega cross omega, so that the meet of omega cross omega operated on identity of omega cross omega, that will be the map from, that will be the internal map from omega cross omega to omega, is the internal meet. Yeah, so I have substituted for B because it's natural. Everything is natural here. So substitute omega cross omega. So the identity has to map to some map. Identity of omega cross omega has to go to some element from omega cross omega to omega. That is our internal meet. If you change this intersection to union, then you will get the internal join. Right? False I already showed you how to obtain the false map. And negation is usually done via composition with the false map. Composition of the characteristic function with the false map. Okay. So you understand all these things, all these properties. They are very nice properties. I will write one more because we have seen something like this earlier. So pullback of an epi is an epi. We have seen this in the category of, in an abelian category, but the proof here is entirely different. Yeah, that actually makes you wonder that what other properties are common between toposes and abelian categories. There are many properties common. In fact, in the next lecture, we are also going to see that there is a characterization, there is an axiomatization like Grothendieck's axiomatization. Grothendieck's definition of Grothendieck categories, you remember? AB1, AB1 star, like abelian category which has AB4, AB4 star and, sorry, AB4, AB5 and the generator. There will be a similar theorem for Grothendieck toposes. And there was Gabriel-Popescu theorem. Gabriel-Popescu said that any Grothendieck category is a localization of a module category. Similarly, every Grothendieck topos, which I haven't defined yet, every Grothendieck topos is a localization of a presheaf topos. Yeah, so there is a lot of parallel. In fact, all of these can be generalized to any enriching category. Like Grothendieck category is ab-enriched world. This Grothendieck toposes are set enriched world. Yeah, you can do it for any enriching category. And I haven't given you many examples of an elementary topos, but we will open with examples of elementary toposes or toposes in general next time. And I will show you what the subobject classifiers there are. Okay, let's stop.